Bertrand speaking. And he's going to be talking about a moment method to solve multi-objective linear programming.
Thank you. Okay, first of all, thank you for giving me the opportunity of being here in this program, which I have found very interesting. The level is great, and the talk has been so far very informative. And I want to talk about an application of moment and polynomial optimization to say non-natural problem, because this is something which has to do with a linear function and polytopes. And this is part of a series of papers that we have been working, and some of them are already published. But this particular research has not been presented yet, although the results are published, because in our say domain, in operational research, as you soon start, even if there are many people which are interested in multi-objective optimization, whenever you start talking about polynomial, people simply switch off, and you don't get the chance to really convey your message. So this is something we have been doing, but we didn't find so far the right audience to present. So I think that this is a good point, and this is when I talked to Jean-Bernard last week about this application. He told me, well, you should present this because probably people will get into the point. So this is why I prepared this informal talk based on the result in the paper, but it would be simple and short. I hope not to go over more than half an hour. Well, this is the outline of the talk, and I will give a brief introduction and motivation why we wanted to solve this problem using those tools. Then I will go to the point how to encode the solution of this type of problem in some polynomial optimization problem, how to use a moment or SDP approach to recover the solution, and I will present some conclusion. Let me start with some formal definition of the problem. And the problem I want to, well, the standard way to present a multi-objective problem in finite dimension is that you are given a function which goes from Rk to Rn, and you are given also a compact set, and you want to find what is called the vector minimum of those problems. And then here the point is that, well, the function is multi-dimensional, so we are trying to find simultaneous point that minimize simultaneously all these k functions. And of course, this vector may not, in fact, component-wise doesn't induce a total ordering in Rk, so that first of all we have to agree on what is considered a solution for this type of problem. In this framework, what I will consider a solution is the so-called Pareto-optimal solution, Pareto-optimal point, and there is nothing but a point that cannot be beaten in terms of values of objective functions. So you cannot find another point which has less than or equal to values to the one that you have found, and at least one of the components is strict. This is what is called a Pareto-optimal point. And finding one Pareto-optimal point is not hard, but the question is that in this type of problem we are interested in finding the entire set of Pareto-optimal points. So this is which is crucial. This type of problem has many applications in different fields like economics or game theory or spatial analysis. In particular nowadays, well, there are many applications where one wants to maximize benefit but minimizing gas emission, or you want to find tessellation or commercial districting so that you have compactness and at the same time you have sharing power, many things that can be considered simultaneously.
So how does it relate to Nash equilibrium of matrix?
In this problem, there is only one decision maker that controls all the objective. In Nash equilibria, each objective is controlled by a different agent, so that you have partial control over the decision variables, and this makes somehow more complicated. The Nash equilibrium problem.
But I mean, this Pareto optimality looks very much like the Nash equilibrium definition.
But in a Nash equilibrium, one agent control one objective.
Yes.
Okay, and then what you are trying to find is that, and you have a function that depends on the decision of every agent. So you control one variable and the other agent control the other variable. And what you are trying to do is, when your objective function, you try to find a point such that if you have no incentive to deviate from the point that you are. Okay, but you only control one point. So in essence, you are solving for you, from yourself, you are solving a single objective problem. Well, here there is only one decision maker that controls all the variables, and he's trying to find the entire set of points that cannot be dominated component-wise.
Okay, so this would mean that you find all Nash equilibria.
No, there are no equilibria here. Because there are no, in the Nash equilibria, you have to somehow we can discuss later, but in the
Okay, can you just go on?
It's related, but it's not the same concept. Okay, I'm going back. All right. Well, today I like to be modest, and instead of considering the general function and general compact set, I will simply concentrate on the simplest case, which is linear function over polytopes. So this will be the framework, and the definitions are the same, and what I like to characterize is the entire set of Pareto-optimal points. This is, the structure of this, the geometrical structure of this set, it's known from a long time, and it has a facial structure, and it's known that the entire set of Pareto-optimal solution it's always a finite union of faces of the polytope. Of course, this must be connected, but not necessarily convex. This is faces. You may have faces of any dimension, from point to complete facet. And it is also known that the computation listing, obtaining a representation of this set is sharply hard. Most of the algorithm, this doesn't mean that you cannot find a solution in many cases, because what usually is done in this type of programming is that, since we have a facial structure, it is enough to construct the vertices of the polytope that are Pareto efficient, and then, knowing the structure of the polytope, you can recover the complete set of Pareto, and somehow this is what is done in most of the algorithms which are available so far in the literature. Let me tell you now why we want to analyze this, what is the motivation of this research. Essentially, is to establish better parallelism in terms of algorithm for solving the single objective problem and the multi-objective problem. I'll tell you, this is, I know that this is an ad hoc classification, and you may not be...
So, what exactly was sharp on the previous experiment?
It's
It's counting of the
counting.
vertices of those
Counting
regions.
is equivalent to counting vertices.
Okay.
Yeah.
But counting the vertices of a polytope is hard.
It's hard, yes.
Yeah. On the other hand, if you just want to add description, this might be easier. No?
Yeah, this is exactly what I mentioned. Depending on the description that you are happy with the encoding of those vertices, you may have it, but if you want to list, then the best you can have, probably it's a polynomial delay algorithm. For one vertex to the next, you need a polynomial time number of operation. Okay, so let me establish the parallelism and why we get to this last cell in the table. Well, in single objective linear programming, we know from the old days that there are different type of algorithms. On the one hand, we have those which are simplex-like, that do pivoting, and then I will call this algorithm active set algorithm. There are primal, there are dual, there are also primal dual, and there are the non-active set that, essentially I will refer. I know that this is a very broad classification. They say that these are interior points. There are many others, but okay. Now, in terms of the multi-objective linear case, at the beginning of when this area started to be developed, Yu and Seleny developed a primal simplex algorithm that was a pivoting algorithm able to generate all the vertices, which were Pareto solution. Later, Stoyer also gave another algorithm. There are some other. This list is not complete. Concerning the dual point of view, also Benson in '98 provided an algorithm that it works in the dual world, and also it's able to generate the entire set of Pareto optimal solutions. More recently, Ergot, Leune, and Shao have provided a different algorithm that is more efficient than the Benson one. And concerning primal dual, together with Matias and Antonio Rodriguez, we also developed a primal dual algorithm for multi-objective optimization that it's somehow good for some particular classes of problem, essentially multi-objective network problems. And there was a question that was proposed, well, was posed somehow. It was several people in the field wonder whether there would be non-active set method able to generate the entire set of Pareto optimal solution. And till now there were only partial answers, and those partial answers were given by Georg Fliege in the two papers in 2004 and 2006. Being fair, Georg provided algorithm for more general classes of problem because he considered not only linear cases but the convex case. So a set of functions that were convex and a feasible set that was also convex. But the answer he provided were that he was able to obtain a number of Pareto solution of the set, but not the entire description. And he uses interior point algorithm. Now the point was, in those days, whether it would be able to generate the entire set not using pivoting algorithm. And this is what I like to consider today. What I will try to do is to adapt technique that has been developed in the world of polynomial optimization just to be applied in the case of linear objective function and polytope.
What are roughly the guarantees of these algorithms? Are they polynomial kind?
No. Pseudo-polynomial.
But so what the output will be?
The output will be the list of point, the coordinate of the point. If you, well, I will get to the point. You might be satisfied with something that encodes the information, still will be non-polynomial, because this problem, otherwise there will be something wrong. Okay, let me illustrate what I'm talking about with this very simple example. This is an example of two objective functions which are encoded in the matrix C, and this is the constraint set, and this is the right-hand side, and this is the feasible region. This is a very simple feasible region. In fact, these two last constraints are simply to say that we have bound on the variable in the primal space, which are also valid in the dual space, so just to have a polytope, because we wanted to convey this to polytope. Well, the optimization here is that we want to minimize simultaneously with respect to x1 and x2. So it's like if we try to find something such that the intersection of the cone pointed at any point in the polyhedron has intersection the point. And then it's easy to see that the Pareto frontier is just this lower part of the polyhedron. Okay, this is how to go from the multi-objective world to the polynomial optimization. Okay, there is a null result that can be traced back to Gas and Sapi in the 50s that applies in the linear case, and if you want to Geoffrion in 68 that applies for convex cases, that says that a point is a Pareto solution if and only if its characterization, if and only if there exists a weighting vector that belongs to the standard simplex in k dimension, such that this point is a solution, an optimal solution of one of those problems. This is the so-called scalarization. This is a standard trick in multi-objective. You have a multi-objective problem, and under some mild condition, all those Pareto points are solution of single objective point after weighting scalarization.
Does it matter if you want an extreme point solution? So x star could be on the line, on the interior of one of those line segments. So it is a solution, but it's not necessarily an extreme solution. Is that right?
No, not necessarily. Well, this characterizes a stream point solution, but no, it characterizes all solution,
Yeah,
all solution,
yeah.
all solution.
But if you only take the extreme points of these scalarizations, then it seems like you should only.
This is what you have to ensure. The idea is from this scalarization. No, here the problem is that you have to solve this for infinitely many lambdas. You have a continuum set of lambdas. Then to get the entire, you will need to solve the infinity many linear problem. In fact, continuum number of linear problem. But the idea is behind this, what we want to do is to find a way to extract a subset of those things that ensure that you will get to the vertices. Okay, so this is again.
I guess for almost all the lambdas, you will only get a vertex, right?
Yes.
In some sense, it is easy to extract vertices.
Yes.
Or it is a vertex, just
A
a
vertex,
generic.
yes, a vertex. Well, there's more. There's more knowledge after that. In fact, one can prove that there is a partition of the parametric space, so that if you go to the interior of each cell and you take a lambda in the interior, this lambda will produce a vertex. But everything depends on the partition, and the partition is not known. Okay, there are some other. I'm not claiming that this is the only way. This is simply an application. We wanted to do an application of some technique. Okay, this is simply, you consider this problem, and this is dual, and now it's again well known that there is, in the case that we have a polytope, there is a strong duality between these two problems, and then one can characterize the solution for all lambdas simply as a system of polynomial equation, because at the end what you need is to fulfill these two conditions, which are complementary slackness. And here you have u and h, so this is a polynomial. So together with those conditions, again, what you could write is that one way to encode all the Pareto optimal solution of those problems is by this system of equation and inequalities. But again, the problem with this system of equation, this equal whatever system, is that it has a continuum of solution, because it encodes all solutions, and solutions are also not all the vertices, but point in the middle of edges, faces, facet. But remember that we were happy just to characterize vertices, so we can somehow impose over those things that we are looking for only vertices, and this is something we can do. There are some questions that still we don't know how to answer. I'll tell you later how to pass to vertices. Those questions have to do with whether this approach is applicable to other cases, not simply the continuous case, but the integer case, where you want to solve the problem and your variables are forced to take integer values, or whether you want to solve more general multi-objective convex problem under convex feasible set. Well, at least the approach that we follow here does not apply directly, essentially because we don't have strong duality in the integer case. So, well, everything is based on finding some equation that characterize solution, and you are in the integer case, you have, in most cases, duality gap. So, in this regard, you cannot apply those things. It is true that in the integer case, there are other tools that can be applied. In particular, it has been proved before by De Loera, Gemeke, and Köppe and later this result was improved by Victor and myself, that one can encode the entire set of Pareto optimal solution in the integer case using sure rational generating function of lattice point in polytope. This is something that is being done, but this is a different story. And concerning the multi-objective convex problem, we still don't know how to handle those things, because the good thing here is that we can characterize the set with a finite number of representatives, the vertices. But in the convex case, it doesn't get, well, we don't know whether it exists or not a structure that allows to construct the entire set simply having a finite number, or which are the point we should consider to reconstruct the entire set.
Well, if you are given, if you optimize over as an algebraic set, the answer is yes, it's possible to encode your answer
In polynomial.
as a set, as an algebraic set.
Yes.
So in that sense,
Yes.
sort of.
No, this is true. Okay, so the way to get to the vertices, to characterize vertices, is simply using the fact that vertices, since we have rational data, have rational coordinate. Then we simply have to do a scale up of the coefficients so that at the end vertices are represented in integer values. And this is simply done considering minimum least common multiple of determinant in the set. You take those scaling factor, you multiply your system, and you will get that vertices will map into integer point in a different problem. And this is what we follow here. And using this scaling, we could prove that the entire set of optimal solution is characterized as a solution of this system. Essentially what it says is this was the original system that I mentioned before, and these are the conditions that we impose on the coordinate of the point that will represent vertices. In the scaling, they will go to integer point, so some of them has to fulfill this equation. And this is if and only if condition, because in the other way, any solution of this system is a Pareto optimal solution after projecting on the first coordinate and dividing by the scaling. Although it is true that it might be that when you project it back, you will project points which are not vertices in the original space. So you may get extra Pareto solution in this representation, but still Pareto. In the example that I presented before, the system that one has to construct is this form. In that case, the scaling is 6 for the primal and 6 for the dual. And, well, this is a representation. It's somehow ugly because you have polynomial of degree 30. But still. Therefore, the important thing is that this semi-algebraic set has a finite number of solutions. This is important, and therefore the ideal generated by those polynomial will be zero-dimensional, and this will be crucial in order to obtain the solution. Then, well, essentially it's known that if you have a zero-dimensional ideal in your set of equation, if you consider one of the problem in the Lasserre hierarchy with the relaxation order sufficiently large, a generic solution of this semi-definite program will encode the information that you need in order to obtain the solution of the original system. In other words, this feasibility SDP is enough to characterize the solution of the multi-objective problem. In fact, one generic solution which lies in the interior of this for n star sufficiently large. This is the trick, but finite, because the the system has a finite number of solutions, will be enough to characterize the solution. And this is what I mentioned before, that in somehow there is a characterization that encode the information that you need to recover the solution simply as a feasible solution in this type of problems. Now, if you want to extract the solution, you want really to construct the coordinate of the vertices in your system, then you should use this matrix moment algorithm, which essentially works with the ideal, and it works well if the ideal is zero-dimensional, which is the case in our type of problem. So if you consider the polynomial that appear in the system that encode the solution, since they have a finite number of solutions, it implies that the variety of this ideal is finite, and there is a result by Lasserre, Laurent, and Rostalski that allows to construct the real radical ideal of this original ideal as the kernel of one of the moment matrices for S sufficiently large, in one of the solutions of the previous system, which is must be generic. And then the way to get those things is using this algebra that since J is finite dimensional, it induces a vector space that is also finite dimensional, and when you obtain the real radical ideal of J, then the dimension of this vector space coincide with the number of solutions in the vanishing variety of your ideal. And well, now what we did is that, well, this is also something which is known. If you consider this linear operator between this algebra, considered as an algebra, and this linear, the algebra itself, and you define the multiplication operator in this term, then using a basis of this linear space, you can write this operator as some multiplication matrix, and then by the Stickelberg theorem, one can recover the coordinate of any polynomial with the evaluation of the polynomial as eigenvalues of multiplication matrices. And then, using that path, if you have T large enough, then this condition is always, for S large enough, this condition is fulfilled. Whenever this condition is fulfilled, then the kernel of the moment matrix in this Y will be the real radical ideal of J hat, and you will be able to obtain all the elements in the vanishing variety of J hat as eigenvalues of multiplication matrices. And the way to obtain the coordinate is simply to consider multiplication matrices of the indeterminate that define the coordinate of your point in the original space. So you will consider this polynomial, which only depends on XL and its corresponding multiplication matrix. You will find the eigenvalues of those things, and this will give you all the coordinate of the Pareto point in the original space. And this is doable. And here is an example. We use Clock-T-Poly for obtaining the solution of the system that I presented before. And what we get were this set of solutions. These are the coordinates for the x's. In the scale-up space, these are the coordinates of the u, and these are the coordinates of the lambdas. Remember that the scaling that we used for the x's was 6, and for the dual was also 6. So it means that these are not the real coordinate in the original problem, because we have to divide it by the scaling that we have using to scale up. Just for information, the relaxation model we have to consider to fulfill the rank condition was 4, and the sizes of the matrices were of this 330 times 330 for the moment matrices. Therefore, since the scaling was 6, dividing the coordinate times 6, we get to this point. As you could see in the table, there are some points that are overrepresented. For instance, this 12.6, 12.6. In the scaling, those points appear twice, but when we project it back to the original, it's the same point, because they combine with different u's and lambdas. So this is what happens when you move, when you enlarge the range of values in the integer parameter. Well, those points represented in the feasible set give you the vertices, which are Pareto, and this is somehow the application that we have found interesting in order to recover this type of set using a different tool, which is far from the linear work. In conclusion, what we have done here is we have applied a moment approach to find the set of extreme Pareto optimal point of a multi-objective linear program. We have constructed an explicit SDP, which is based on the Lasser hierarchy that encodes in every generic solution all the information required to construct the multi-objective set. It is also shown that we can get those points using this moment matrix algorithm. And well, as a message that we have found interesting is that there are some nowadays very powerful technique in the field of polynomial optimization that could be applied in other areas, giving some interesting results, particular this type of results. And this is all. Thank you.
Is there any questions from anyone?
So a polynomial equation system which you set up has only finitely many complex solutions, I guess, right?
I don't know how many solutions, because we only look at the real.
But for the method of Lasser, Laurent, etc. to work, don't you need that you have only finitely many complex solutions? Because if you go to a quotient algebra, it should be finite dimensional, and this means there is only finitely many complex solutions.
Oh, there's actually the methods.
You don't
methods from real algebraic geometry that would produce your real roots if you are giving it an ideal with finitely many real solutions, and you can just
what you use here is not the
deformation of it.
It's not the radical ideal of the J. It's the real radical.
Yeah. But the algebra, that was the other question, in fact, because you had this J hat, but this was not the real radical ideal, it was the initial ideal.
No, but yeah. So no. You in this is what you use at the end is not the. This was just to comment on the algebra, but what you use to construct the solution is the quotient with respect to the real radical ideal, and this coincides with the kernel of the moment matrix of any.
Okay.
So it's not on the. This was simply to illustrate the algebra that is used, but you have to make the quotient with respect to the real radical.
Yeah.
So, have I understood you correctly that sort of this just step number one is you have to enumerate all the vertices of your polytope and then do this you make them all integer by multiplying by
Yes.
that constant, right?
Well, no, you don't know which are the vertices. You don't have to enumerate them. No.
I mean,
You don't have to enumerate them. You only have. You simply take your system and multiply this. You scale up the system so that in the new coordinate, vertices will have integer solution. But you don't know which are. Simply you enlarge the range of integer values so that any vertex, when you scale up, will go there. You would know. You would not need to do anything.
So that integer, presumably it's related to the determinants of every possible
Yes.
basis, every possible prime or feasible basis.
Yes.
There's a fast way to compute it, is there?
No, it's not a first, but you can get upper bound.
Okay, right.
Everything it's theoretical.
No,
It's
yeah.
not. I mean, I'm not claiming that this is something which is competitive. It's,
So what I wonder is that you actually need that. It's a bit strange because you have a formula that just says that there is no x such that something happened, right? So you should be able to write a positive Stellensatz statement saying that such x does not exist, right?
yes.
So then just
Yes.
write it down and extract what you need from it without any blow up that you have to do.
It might be, but this is a good question. I didn't think of this.
No,
It might be
yes.
possible. Yes.
Just that was something that
it is a good
jumps
point.
into mind.
Yeah, it's a good point.
So if you just look at the two objective functions, so just P criteria problems, so then this theorem of Saat would say just take lambda times the first plus 1 minus lambda second, so it's just really a scalar that wanders between 0 and 1, and does this bring any simplifications that you can exploit or not really?
In the by criteria,
Yes.
well, in the by criteria there are many things that you can do. In fact, in the by criteria, what you have is a segment for the parameter space, and the partition is very simple.
So it's not point to go to
No.
polynomial optimization.
No. In the two criteria, you only have to identify segment.
Yes,
For-
yes, that's what I meant, yes.
And this you can do it very efficiently. But when you go to higher dimension, you don't even know how to
Yes.
move from one cell to another
Yes, okay.
without repeating.
So the back criteria is really much simpler than say
Yes.
3 criteria or
There is
beyond.
a jump between the two criteria, which is well understood, to the third dimension. In the third dimension, things become.
I've got another question. Okay, so the degree of the polynomial you really, the size of the matrix that you really need could be very, very large.
Yes.
If you put a bound on the degree, so you choose a matrix which is smaller, and it doesn't solve the problem, does a solution to that SDP still give you some useful information at all or not?
I don't know.
All right.
I haven't thought of that. It might be. I don't know. It's a good point. Yeah, there are some other issues that. Yes, this is a good point.
So the rating of the number of k as being small compared to the dimension of the polygon or the dimension of the space, or is it?
In practical application, you mean, or in general?
In practice,
Yeah.
I guess
In
it
practice,
should be
yes.
small, right?
In general, this is a mathematical object. You could take.
But also the
You could take
just-
n divided by 2 as a number. So,
So-
the same complexity.
So what about this P sharpness result that you mentioned? Is it only holding when your number of criteria is big enough compared to n?
A good question. I will
I guess
have
for
to look.
Two parameters.
for
should
two parameters,
be-
not. It's not.
Is it?
I think that.
Because can you sort of get all the vertices of your polytope as answer?
Yes, but then. Yeah, you're right. Somehow you're right. But
It's
everything
also
which
all
I was. I wanted to be not very precise. For this to be applied, you have to ensure that the null cone condition doesn't apply. It means that the normal vector to the objective function do not generate the zero. So zero is not in the interior of the cone generated by those, because in that case what you get is the entire. And then I cannot tell you exactly, but we can check the chapter. This result is by Köppe and Hemeke, I guess. So this is one can check.
Some result says that if you sort of discretize the lambdas, find to some reasonable accuracy, and then look through all of them,
You
then
will
you get
find.
all the.
Yeah, you will approximate. Yeah.
Because like when you think that if you have like k coefficients for the k different functions, then something like 2 to the k.
Yes. Yes.
Lambdas.
You are right. Exactly. This is good. Mm-hmm.
No more questions? Thank you for very interesting talk.
Thank you.